Okay, I'm Jaden. I'm coming from Kalamazoo College in Michigan, and I'm a part of the Joukowska Lab.
Awesome. And would you like to give us a brief introduction and kind of tell us about all the hard work you've been doing this summer?
Yeah, totally. So the Joukowska Lab is particularly interested in drought resistance and drought tolerance. So our model species were Arabidopsis and cowpea. And so essentially, the lab has previously identified two metabolites of interest that are found in higher abundance when the plant is under some kind of drought stress, right? So we wanted to see, well, why is that? What is the plant? What is the metabolites doing? What is its role in mitigating drought stress or, adding to the susceptibility of drought? So to do that, we had to find the effective concentrations of each metabolite that would not be too much that it would kill our plant, but just enough so that we see an effect. And so here we have two agar plate assays where we did on Arabidopsis. So here we have varying concentrations of both cineal and N-acetyltryptophan. And we can see that every concentration of cineal decreased root length, while the first three concentrations of N-acetyltryptophan actually significantly increased root length. And so this was great. So it allowed us to select this concentration here, which was the concentration of cineal that we saw had the least amount of decreasing in root length. And this concentration here, where we're able to see the most amount of significant root growth, but not too much where it's killing our plant. So once we were able to identify the concentrations is when we were actually able to start applying osmotic stress and drought stress to both Arabidopsis and cowpea. So for Arabidopsis here, we have varying concentrations of PEG, which is basically a solution that's high in solutes, right? So it causes osmotic stress to our plant. And so here we can see that our most significant results are actually when you compare our NAT and our control at 75% PEG. So this graph is basically showing that NAT, while it's paired with drought stress, has the most significant effect on decreasing root length. Here, we tested it on cowpea, and we tested multiple parameters, including shoot size, evapotranspiration rate, chlorophyll content, photosystem 1, photosystem 2. And overall, we can see that when NAT is paired with drought stress, it is causing more susceptibility to drought in our plants. So future directions, if we can figure out a way to solidify these results and then find a way to even stop the endogenous production of an acetyltryptophan, then we can perhaps engineer plants to be more tolerant to drought.
So that's so exciting. This is fantastic work. I'm so excited to see some of the future directions that you mentioned at Monday morning seminars. Was there anything here that you found super surprising that you weren't expecting necessarily?
I guess I wasn't expecting the N-acetyltryptophan to have such a negative effect on our plants. I was actually expecting that the NAT would help our plant in the face of any type of drought stress, while actually we can see that we have intraveinal chlorosis occurring on our plants treated with NAT. We have lower amounts of our shoot size is significantly decreased. Things like EVT, though, are not affected, evapotranspiration rate, which I also thought was surprising.
Yeah. Thank you. And you mentioned a ton of different methods that you'd learned or been a part of this summer. Was there any one that was your favorite, that you enjoyed the most?
Honestly, I really like being under the laminar hood. So I didn't love plating seeds, but I don't know. There was something about being under the laminar hood. I felt really like, well, I'm really here, So I don't know. That was enjoyable to me. Yeah.
That's awesome. Thank you so much for sharing.